Hello, my name is DK Ezekoye. I'm a professor of mechanical engineering at the University of Texas at Austin. And I'll be teaching the module on fire safety and fire science as part of the nuclear engineering PRA for fire. And the PRA is, again, probabilistic risk assessment for fire issues in nuclear power plants. The syllabus is displayed on the accompanying screen, and I'd like you to note that the instructors for this class really are myself and Ting Ma and J.D. Brown from Oklahoma State University. So as we look at the syllabus, I'm going to scroll down in the syllabus. The syllabus gives certain texts for you to take a look at, to read. It's a mixture really of easily accessed online material. These are the Nuclear Regulatory Commission guidelines, these NUREG documents, NUREG 1805, which is Fire Dynamics Tools, NUREG 1934, Nuclear Power Plant Fire Modeling Application Guide, etc. But then also there are two textbooks that I have there as recommended. And these recommendations are Fundamentals of Fire Phenomena by Jim Quinteri and An Introduction to Fire Dynamics by Dougal Drysdale. And you can find either of these books in your university library. So I would like you to download the following. And so these downloads are, again, between the reports that I've talked about and other computer software tools that are useful for some of the problems that we're going to be looking at. And so these can either be found on the NRC website, nrc.gov, or the National Institute of Standards and Technology website at nist.gov. And as we go through these modules, there are essentially 15 modules. We will discuss how to use these different tools and, again, the details of getting them, setting them up. Okay, so what's the basis of this class? What are the issues? Really, the objective is to allow students to become familiar enough with fire science issues, fire phenomena, that you can understand what kinds of hazards and threats fire poses within a nuclear power plant. So really, we're going to understand the fundamentals of fire and fire thermochemistry, understanding that none of the students in this class necessarily will be an expert in fire science, but again, with the hope that this will provide some clarification of what, again, these underlying issues are in fire. So topically, we'll look at combustion thermochemistry. What are the fundamental combustion issues that drive fire? And the thermochemistry is this mixture of thermodynamics and chemistry. And so this is, again, static in the sense that we're looking at equilibrium issues, things that don't necessarily depend on rates. Then we'll look at combustion kinetics. We'll understand how we go from rate-independent equilibrium approximations to kinetics and the aspect of rate in dictating how a particular combustion process occurs. Now, the conservation laws are essential when trying to model any physical system that involves fire. So we'll talk about mass conservation, momentum conservation, energy, and species conservation. In all sorts of fire applications, the notion of flammability is central to our understanding of how a combustion process or a fire process evolves. So this is going to require us to better understand what flammability limits are, what flammability implies, and the issues associated with it. We'll talk about the different types of canonical flames. So there are premixed flames, flames where the fuel and the air are initially intimately mixed, and non-premix or diffusion flames where the fuel and the oxidizer, in the cases that we're generally interested in, it will be an air gas where oxygen is the primary oxidant. But again, we'll talk about the details of these different types of flames, and then we'll really progress into more system-looking discussions about ignition processes, ignition of liquids, ignition of solids, and there's going to be a lot of heat transfer there. We'll provide the background and heat transfer that you're going to be required to analyze this. And then we'll transition to looking at, again, more engineering technological issues in terms of flame spread over different types of materials, and also the impact of fire on compartments. And so we'll discuss what the implications of this. All right, so later on, again, just to summarize, we'll talk about computer-based modeling of fire in compartments using a couple of different types of examples of computational models. So this fire science portion of the fire probabilistic risk assessment class is composed of 15 one-hour lecture modules, one-term exam. We're going to have homeworks every 3 weeks, every three sets of lectures, and a final project, no final exam. So looking at the calendar in more detail, what you see is that really in this first lecture, I will be discussing, again, giving a broad overview and introduction of how fire impacts the nuclear power industry, and then we'll talk about, again, diving into the details, starting with combustion thermochemistry and basic issues in chemical balances and stoichiometry. And this is really a review. You've all seen that these issues from really your first chemistry class, and we're just going to use that as a basis and build on that until we're able to get everybody to the same point with respect to combustion science and then fire science. Okay, well, this is timely in terms of our discussion about fire impacts on the nuclear power industry. I'm going to switch to a document camera, and in the document camera, I want you to note that what we're showing here in the document camera is the latest issue of the Society of Fire Protection Engineering's magazine, this Fire Protection Engineering. And in this latest issue, this third quarter 2012, the cover discusses this notion of achieving compliance, fire protection at U.S. nuclear power plants. This is something that fire protection engineers are very aware of, very interested in learning more about what the issues are in nuclear power plants. As nuclear engineers, at the same time, it's extremely important that you start understanding what the issues are in terms of basic issues in fire. So we're, in some sense, coming from two sides at this to, again, better understand what exactly what's driving these different issues. So I'm going to be using a tablet to write notes on, and so based upon that, I'm going to sit down and we're going to start talking about, again, some of these different issues here. So I'm going to switch the source to this laptop, and we'll get started. So. Okay, so why are we interested in looking at fire and nuclear power plants? What are the issues? What are the safety implications of fire in these types of environments? So let's talk about that a bit. So fire and nuclear power plants. So there's the why. Well, really, for all types of power plants, fire poses significant possibilities for loss and for damage to the plant. In the nuclear industry, as you know, the consequences of fire and the consequences of any sort of the distribution of fire gases that may have contacted materials that are radioactive poses even more significant consequences and danger. In general, the types of things that we have to worry about in nuclear power plants are very similar to the fire risks that exist in other types of facilities. It's really the cascade of the damage associated with the fire that is what one has to be particularly concerned about. And there are other parts of this class, not the fire dynamics piece, that will address the consequence modeling in detail. So the issue again is that the consequences of fire pose significant risk and hazard. And again, this is similar to other types of power plant facilities and power facilities. Okay, so one of the things that we'll look at in detail really is the evolution really of fire. So, what is it? How does it evolve? What are the stages in which there can be mitigation? So, as we look at the evolution of a particular fire, we can really provide points that we can look to assess what the overall damage and, again, steps to do mitigation might be. So I'll first talk about this in perhaps a more familiar type environment, and this is a compartment fire within say a residential structure, so a house. So as we look at fire within a structure like a house, so I'm going to draw a house here or a room within a house and talk about the different steps and the different issues that one might be concerned about. So we have a room in a house. This is upholstered furniture fires represent one of the major sources of fire damage and hazard in a room. So there's a sofa. No one has televisions that look like this anymore, but say a television. And unfortunately, smoking and smoking-related activities are a major source of fire. So imagine an unintended ignition source, and so there's some smoking ignition source that is laid on this piece of upholstered furniture. So really, again, the starting point of any given fire is some sort of an ignition process. And so as we look at this ignition process, the ignition process is the coupling of a heat transfer process and a thermochemical degradation process. So I'm going to abstract this as some sort of heat source in close contact with some condensed phase material. So this condensed phase material for a sofa is polyurethane or some covering whether it's cotton or some synthetic, above the polyurethane. So what happens here is that the heat transfer process from that heat source, so this is a hot resistive element in the case that I've abstracted it, this thing heats up the polyurethane or whatever polymeric material we're looking at. And there's a so-called pyrolysis process that occurs in depth. And pyrolysis, in this case it's a thermal pyrolysis process, simply means that all the different molecules within this polyurethane are thermally excited, and in that thermal excitation they start to shake and eventually they start to break. So we break bonds because of this heating process. So we have thermally initiated degradation. And what happens is that we release small fragments of smaller molecules that percolate through this porous medium, through this polyurethane, again, because of the heating. So now we're going to draw this a little bit differently. We have this heat transfer process. We're going to use the notation Q dot double prime for a heat flux. So this is a units of which are watts per meter squared. The double prime in the notation that we're going to use, I'll try to be consistent, will suggest that it's a flux or something on a per unit area basis. And so again, this heat flux initiates chemical degradation, again quite complex, within this condensed phase material, which becomes a source for volatiles that percolate through the material and come out. So we're going to say that there's an M dot double prime. This is a mass flux of the volatiles with units kilogram per meter squared second. And it is in fact these volatiles that we consider the fuel for a fire scenario like this. So we have an ignition source that is intimate with a condensed phase material. It heats the condensed phase material until in-depth pyrolysis occurs. The in-depth pyrolysis creates this mass flux of volatiles. And at this point, we haven't said that there's a fire yet, but we simply have said that there's a mass flux of volatiles. So really the next steps are what happens to this volatile mix as it's coming out. Well, experience says that if you have a flammable material vapor, that alone obviously is not enough to create a flame, but it is the availability of this flammable vapor in an oxygen or an oxidating environment with some pilot, as we would call it, some heat source that will allow the reactions to take place. That is, that allow the reactions to overcome some chemical energy barrier. Then all of a sudden we're poised to have a combustion process, a flame. So again, this abstraction says that we have this mass flux of volatiles evolving. And now I'm going to use this notation F because I'm going to suggest that this subscript is that these volatiles coming out are actually the fuel. Now, in a normal gravity environment, these volatiles are hot because we've used a heat source to actually create them, and so buoyant acceleration is causing these things to rise, and they're in a cooler oxidizing environment, so there's a mixing process taking place where we're actually mixing in air, which is composed of nitrogen and oxygen. And so now all of a sudden we're creating this mixture of something that is in fact flammable. And as soon as this flammable mixture sees a heat source, and the heat source may have been that initial pilot, that ember, or that part of a cigarette or smoking, again, something that's part of a smoking device that causes the ignition of this flammable mixture. So again, eventually the flammable mixture encounters a heat source that drives a reaction. So that drives a reaction that overcomes some energy barrier that we'll talk about shortly and ignites a flame. And now we haven't said what a flame is yet, and we're talking sort of generally at this point. We're painting a picture of what types of issues come into play. So at this point, we really haven't said what a flame is. So I'm going to say, what is a flame? At this point, I want you to think about a flame as an interface. And there are increasingly more sophisticated, more complex definitions for flame. And in some sense, I would say that perhaps we really can't define it using words, but we can certainly define it using equations and mathematics. So really, when we really talk about flames, we're going to have to talk about flames within a more mathematical context and using mathematical descriptors. But right now, we might imagine that a flame is an interface. And there are different types of flames. But the initial flame really that we will likely see in any kind of ignition process is something called, again, a premixed flame. So when we talked about this flame, we talked about fuel and air intimately mixed prior to seeing a heat source. So the intimate mixing says this is a premixed flame, and then immediately after we ignite it, we get an interface between things that, and so let's draw that. So I'm visual, so I'm going to impart on you my way of looking at these types of problems. So I have a fuel-air cloud mixture that is surrounded by a sea of air. And all of a sudden, I have, near that fuel-air mixture, I have a hot spot. And so what happens is that as I put that hot spot at that interface where this is flammable, I'm going to get a burning process that takes place. And that burning process is going to convert parts of that fuel-air mixture to products. So parts are still fuel and air. I have air. And of course, I don't have a clean interface here because diffusion happens, and we'll talk about that. But in some sense, this bubble that, there's growth over here, this bubble becomes burned products. And again, of course, the sea of air. So the premix flame really represents an interface between reactants and products. So that initial flame can be thought of again as an interface between cool reactants perhaps cooler reactants and hotter products. So maybe this is the first time we can start talking about, well, if we were to write some sort of balance equation, some sort of transfer equation, what would we write? Well, we'd say that reactants go to products, and that we're going to again use terms that we're going to define more precisely, but that this process is exothermic, so that it's energy liberating. And that is in fact, one way of discussing and describing this flame. Now, I went through the trouble of drawing this cartoon of this house with this sofa that somebody put a hot material on a cushion. So let's think about that a little bit more again. So we have this contact of this smoking material and this condensed phase material. And I told you that there is this degradation process that occurs, this pyrolysis process that occurs. Well, it's not always the case that we'll get this immediate ignition. So a couple possibilities exist. The possibility exists that we may get something called a smoldering reaction. And we'll talk about what smoldering is, but smoldering at the basic level is a surface type reaction where we don't see gas phase flaming and gas phase reactions. So when you have a charring process, when you see something on coal particles or on charcoal or some in-depth porous media reactions, sometimes that is really looked at as the slow smoldering reaction. So we can have the smoldering process, or we may have had this initial flaming ignition quickly, quick transition to a flaming reaction. So we may have flaming or smoldering. Now, or actually, this may have been a significantly treated, so whether it's flame retarded or non-combustible material, and nothing happens. So there's a possibility of just extinction. It extinguishes the smoking material because it's not flammable itself. But really, we're thinking about this threat issue, and so the threats proceed down this way. Now, any smoldering reaction can transition to a flaming reaction, so there is a possibility of the smoldering reaction transitioning to flaming, or the smoldering reaction to extinguish. So there are paths to extinguishing just for the smoldering reaction. Now, when we have this small kernel of a flaming reaction, let's talk about what is occurring there. So now all of a sudden we're talking about a solid material. We put this ignition source close to it, and because of the mixing of the pyrolysis gases with the adjoining oxidizer, there's a flame, a premix flame initially, that sits above it, this initial flash of a premix flame that consumes this initial amount of fuel that had been liberated in the pyrolysis process. Well, again, lots of different possibilities exist, but unfortunately one process that could occur is that we all of a sudden set up something called a diffusion flame. And so that diffusion flame might sit on top of this material, and what it does is the diffusion flame that all of a sudden sets up on top of this piece of material is using its power to heat up the material and causing that in-depth pyrolysis process that we talked about before. So all of a sudden we've switched from a scenario in which the external heating element is causing the pyrolysis to occur to one in which the flame that we've set up as a result of the initial ignition of these degradation products becomes self-sustaining and begins to liberate more and more pyrolysis gases that will then continue to burn and sustain itself. So now we're in trouble. So we have a diffusion flame, and where that diffusion flame is an interface between fuel, these pyrolysis gases that are liberated by heat transfer processes and the chemistry in the condensed phase, and an oxidant. Again, our oxidant is air outside. Now, the process that occurs is called a flame spread process when we have this diffusion flame sweeping over this surface and continuing to degrade it and create more fuel to be burnt in the gas phase. So this transition becomes a flame spread process. So now that initial flaming causes this flame spread process to occur, and flame spread, just as the name implies, just suggests that we have this spread of a flame. Because, and you know, flame spread happens on many scales, and sometimes we may even view something like a wildfire, a grassland fire, or even a canopy fire in a forest fire as a flame spread process. We have large-scale flames sweeping over condensed phase fuels where the flame heat transfer processes are liberating pyrolysis gases or decomposing this cellulosic polymeric material into smaller hydrocarbons that are then burned in the gas phase. So while scale is important, in some sense the abstraction and the picture are quite similar. So now we have this flame spread process, again, so let's draw our sofa. So we have our sofa where, again, we have flame spread over our, so we have this initial ignition, and now we have this flame spread process occurring. Now, as this is occurring, we're lofting products of combustion into the room, and there's mixing that's happening. We're spreading the burnt products, and these burnt products are composed of all sorts of different gases. I mean, you think about a synthetic material, any kind of polyurethane or any synthetic polymeric material. There are all sorts of bad things, really, that are being lofted into the air as a result of this burning process. In some sense, the flame in a fire is a terrible incinerator because the material is very, very poorly mixed. It's not a very efficient mixing process. This inefficiency means that we're not breaking down these materials to just water vapor and CO2. We have a lot of incomplete products of combustion, many of which are quite toxic and pose a whole range of health risks associated with them. So the flame spread process and the buoyant plume that's generated by this combustion process are really the first indicators that we can are part of the physics that we can use in terms of detection and alarm systems. So now, so sort of from the scale of the room, again, the sofa burning is producing this plume, and this plume is rising because we have a lower density gas than the cool gas in the room. So, we'll talk about the fact that the smoke filling process looks a lot like filling a bucket with water, except that, of course, in filling a bucket with water, the water is denser, and so G, we turn the picture upside down. But what happens now is we can start talking about perhaps alarm and suppression systems. So maybe I have sprinkler heads in this room. So I may have a smoke detector, and I may have things like sprinkler heads. Well, sprinkler heads and smoke detectors are placed, not surprisingly, on the ceiling of rooms and enclosures because of this buoyancy effect that we're exploiting. And so the incomplete products of this combustion include aerosol particles, smoke particles, which are really carbonaceous materials because of this incomplete combustion. And the smoke detector will respond to those, and we'll have a lecture on these detection processes towards the end of these 15 lectures. So the incomplete combustion products include smoke aerosol particles. And again, that's the basis for detection here. The sprinkler heads are thermal devices. They're thermally fused devices, so there has to be a hot enough plume, a hot enough gas temperature at the ceiling level to activate this. And there's a physical process called a ceiling jet that runs across the ceiling. So it looks like a gravity wave where, again, in this case, it's a low-density gravity wave that's sweeping across the roof. Across the ceiling. And so the ceiling jet interacts with the smoke detector and also with the sprinkler heads. Now, in the language of fire, this initial flame spread process that we have here is abstracted as something called a pool fire, really. So we think about this as a pool fire, where pool fires, when they're studied in the laboratory, really it's a pool of some flammable liquid that creates some nice structure. So it's not spreading; it's just sitting there. It's flapping, but it's an abstraction of this problem. And so we'll talk about pool fire physics in, again, more detail. So as this flame spread process occurs, it's going to spread because of the adjacency of all these different fuel elements on this sofa. There are going to be issues, though, because flame spread relies strongly on the orientation of the fuel bed relative to the flame spread process. And we'll talk about this when we talk in more detail about flame spread, but buoyancy, wind-aided flame spread is faster than opposed flame spread. So it's much easier for a flame to spread at an inclined angle. So if we have this flame spread process, this is a lot easier because we're getting a flow associated with buoyancy that's just pulling this and pulling the flame and helping in terms of the spread process. So we're getting heat transfer from the flame downwards as compared to what might occur if you're trying to spread in the opposite direction. So spreading in the opposite direction is challenging because, again, the flame wants to stand up and move in this direction, and so you're not getting quite as much flame area as what you're getting in the case where the flame is spreading upwards. So why I point that out is that it's possible that the flame actually can't consume some of the portions of the sofa because of a downward flame spread process. Okay, now moving on, just these general descriptors of compartment fires and the evolution of a compartment fire. I'm going to go back to this diagram, and I'm going to, again, just sort of redraw that down here. But what will happen is that, remember, it's unusual to have just one, what we'll call fuel packet. So we might think about this as the first fuel packet. And anything else in here might be some sort of secondary fuel packet. And there are lots of possible other packets. It could be just the carpeting in the room. There could be wall coverings. There could be drapes. So there are all sorts of different fuel packets within a compartment like this. Okay, so we have our compartment. Again, we said that there is a flame spread process that has taken place on this sofa. And now let's assume that the sofa we're deep into this, and the sofa is very much consumed by this fire. In that process, it's an enormous amount of smoke has filled up this upper layer, and so in fact there's an evolution of smoke that's filling, and if the window and doors are open, that eventually spill out of this compartment and actually continue to burn because they're unlikely to have had enough oxygen to have burned within the compartment. So we have hot products leaving the compartment through the upper layer and cold oxidizer flowing in through the base. So this smoke filling process and the change in again, this is going to be considered a very high temperature upper layer. So T upper is larger than the lower layer temperature. And there's a lot of radiation. This is thermal radiation. That's because we have this dark, hot cloud of smoke and products in this upper layer that are radiating throughout on all the different parts of this compartment. What that can do, and what that often does, is it sets up the possibility of ignition of secondary items, and also leads to the a phenomenon called flashover, in which the heat flux, so the incident flux from this upper layer is so large that it can ignite remote fuel packets, and that's sort of geometrically remote in terms of the distance from this primary ignited source from each other. And again, what happens is all of a sudden you start getting liberation of fuel everywhere in the room, and you get an extremely fast combustion process within the room that often spills out outside. So there's a transition to this flashover phenomenon that's possible. And one of the concerns with flashover, again, this whole room involvement, is that it can cause a fire to transition from just being locally confined to the room of origin to having impact and damage to much larger parts of the overall structure. And it can also penetrate into void spaces within the structure to create a much more difficult firefighting exercise. So this flashover, again, is whole room involvement. And there are a whole range of problems that are associated with that transition. Now, not all fires proceed to flashover, fortunately. And so there are a lot of different ways that the fire may not have proceeded to flashover. So again, we had the possibility of smolder, this extinction process just because it never transitioned to flaming, the possibility that it was a flaming reaction with flame spread. So what can happen here is that we can have really an extinction process because we get a small item burning within a large environment, and it simply burns itself out. So we can have the fire contained to the initially ignited fuel packet. With no real damage to anything else. So again, this goes towards this extinction side. We can have, again, secondary ignition of adjacent packets. And obviously, there are still paths that it may be simply contained or confined to just those two. And we can have, now all of a sudden, we can have an interesting process where it's extinguished, not necessarily because there weren't adjacent packets around it, but because the compartment is so well sealed that the amount of oxidizer that you produce, the amount of fuel that you produce is so much larger than it consumes all the oxidizer in the combustion process, and because the doors hold, the windows don't break, no new oxidizer flows into the compartment, and in some sense it burns itself out. So all of a sudden we're left with a lot of smoky furniture or fuel packets, but no more fire. So this process could be because of some sort of what we call fire a ventilation limit. That is, we may be able to put out the fire simply because the windows and the doors hold. So that's a possibility. Or if, unfortunately, these windows and doors, windows and doors remain closed, if these are open, then we'll always have an adequate amount of oxidizer, and this may be the path, again, to this flashover type event. Now, again, hopefully, suppression systems, so whether it's ventilation limited or not, hopefully, again, from a mitigation perspective, there are other types of suppression systems that may be able to, again, detect the fire and activate and cause this transition, cause this whole process, again, to be swept towards extinction. So what we've been doing and describing here is a pathway for a fire to move from some sort of ignition source to a much larger, much more damaging process and phenomenon. And so, as we said, there are places and pieces of this that we'd like to examine in more detail. So, we need to understand smolder physics. What is a smoldering front? We need to understand what this flaming reaction means. So what does ignition mean in terms of flammability limits? We need to really look at flame spread in a lot of detail. And flame spread is a major concern, again, in nuclear power plants because of cable tray fire. So if you have cables where the cable covering or housing is flammable, and you have a flame spread process on that cable, there's the possibility of creating what are called hot shorts, where the cable insulation is burned away. So if we have some sort of cable tray with, say, copper wire with some sort of insulation around it, and we have adjacent copper wire, again, insulation. So this is a cross-section of a wire. where we have all of a sudden a flame spread process. So if we're looking, say, from the bottom of this, and so we have these adjacent wire elements. Now, all of a sudden, if we have a flame spread process where the flame is proceeding on this, over this insulation material, this covering, and burns it away, then all of a sudden we have the possibility of these copper wires at some point maybe contacting each other with no insulation and creating potential shorts. I mean, the insulating material is there for a reason to minimize that. And so all of a sudden now, even if these aren't necessarily power cables, if these are control cables, whether it's for a pump or some sort of valve actuator, and we fail this because of a fire, then some of the control mechanisms within the reactor have been compromised. So there's need for redundancy in design to address the possibility of flame spread over something as simple as wire trays, where again there are impacts to the flame spread and the degradation process of that material. Okay, so beyond flame spread, we want to look at compartment fire physics. So the development of the plume, the development of the sealing jet. Remember, the sealing jet is that gravity wave that travels over the ceiling of a compartment. We want to understand the physics of smoke detector activation and understand the physics of something as simple as a sprinkler activation. And then we want to sort of think about what it would mean to be able to actually simulate some of these different physical processes. Okay, in the last few minutes, what I'd like to do is just talk about what we're going to do next. And what we're going to do next is again, combustion thermochemistry. Where we're going to expand on this idea of reactants to products, where we want to fill in the details of what types of materials constitute these reactants, what types of materials are these products, and also fill in the details of the chemical balances, the amount of energy that's released in these types of reactions, and methods of solving for some of these details. Okay. All right. So thank you for your attention in this first lecture, and we'll continue with lecture 2, again, where we begin talking about the details of these systems.